Hello. This is a talk about the possibility of getting a quantum speedup for gradient descent, although the title gives away the conclusion. This work was done in collaboration with my colleagues Ankit, Garg, Robin Kothari, and Praneeth Netrapalli, while I, Suhail Sherif, was an intern at Microsoft Research. So gradient descent was introduced in the mid-19th century by Cauchy, and it's a simple idea for trying to minimize a function that you have only local access to. You start off with computing the function at a point, then you compute the gradient at that point. The gradient is a vector which shows you the direction of steepest ascent along with the magnitude of that steepness. Then you take a step in the opposite direction with the hope that you're actually decreasing the function value. And then you continuously do this step, and at least in this case, the function value seems to be decreasing. It's a simple algorithm, and it's actually used in practice a lot as well. And this is because of the cheap gradient principle, which says that if you can compute a function in a structured way, then with a small overhead, you can compute its gradient as well. So, for example, in neural networks where there are lots of parameters and we want to find parameters in which the loss function is minimized, you would use gradient descent. When you try to abstract out the process of gradient descent, where you just have access to a function value oracle, you also need access to a function gradient oracle. Because at least for high dimensional functions, computing the gradient is not easy if you can compute the function value in a black box setting. The question we want to ask is there a quantum advantage to be had? And it turns out that it's not a ridiculous question. For instance, using quantum algorithms, you can actually find the gradient with one query to the function value oracle, regardless of the dimension. So one could hope that perhaps with less than k queries, we can get the result of k gradient descent steps. If this were possible, this would put it among many other useful subroutines that actually do have quantum speedups. But if it's not possible, is that an interesting result, saying that you have to use k queries to get the result of k gradient descent steps? It sounds like a stringent requirement. So we'd want a formulation in which a negative result would actually be interesting. So we want a task that gradient descent solves that quantum cannot solve any faster. So the question is, what is it that gradient descent really accomplishes? Without getting into the details like the gradient descent steps. And a pretty good fit for this is convex optimization. So in convex optimization, you're given a convex region, which we'll assume is a ball for the purposes of this talk. And you're given oracle access, by which I mean function value and gradients, to a convex function f. And we want to know what is the point at which f takes its minimum value. This is impossible to solve. It could take arbitrarily many queries. So instead, you relax it and you ask to find a point in this convex region, which need not be the optimal, but where the function value is at most epsilon more than the optimal value. For instance, these functions here, where we want to just find one of these red points. Now it turns out this isn't enough to specify the problem as well. Even under this specification, you could take arbitrarily many queries. So another thing that you need to know is how steep your function is. For example, the function on the right here is just a scaled version of the function on the left, scaled by a factor of 3. But you can see as a consequence of this, the epsilon optimal points is a much smaller region than it is on the left. Of course, you could scale it back to make it look like the unscaled version, but even then, the fraction of points that we are interested in is a much smaller region. And this is, so for example here, since we've scaled by a factor of 3, on the right side here, we're looking at the unscaled function, but we're trying to optimize it to a precision of epsilon by 3. And this is a general thing, so we can just assume that the functions we're trying to optimize have slope at most 1, and we're trying to optimize them in a ball of radius 1. And the actual values of the slope and radius, we can just push into the epsilon parameter. So we're just going to assume that all our functions now are 1 Lipschitz in a ball of radius 1. Now convexity guarantees us that if you take the gradient at any point, that is if you take the hyperplane that is tangent to that point, it stays below the function at all points. However, convexity doesn't guarantee that such a tangent exists. So for example, you take the smooth function, there are points where there is no tangent. So here, we have multiple planes that do pass through this point and that do stay completely below the curve. So any of these points is a valid subgradient. And instead of having a gradient oracle access, we're going to have access to a subgradient oracle. So that specifies our convex optimization task. The question is, what algorithms do we know for convex optimization? Now, in the one-dimensional case, we can actually perform a binary search. You find the value at one point, you find out in which direction the function decreases, and you just have your space to just within this region. Now we can continue this and find smaller and smaller values. The question is, how many steps do we need of binary search before we find an epsilon optimal point? Since our function has slope at most epsilon at most 1, the set of epsilon optimal points is going to be at least an epsilon ball around the minimum. And we're going to land within this epsilon ball within log 1 by epsilon steps. And this is the best you can do. For an n-dimensional function, can we still do binary search? Turns out we can. There's the center of gravity method, which essentially cuts down on the volume in which you're searching by a constant factor at every query. But the number of queries it needs to actually reach an optimal point is actually large. The epsilon optimal points can just be an epsilon ball around the minimum, which has a volume 1 by epsilon to the n. So the number of steps is here n log 1 by epsilon. It depends on the dimension. On the other hand, gradient descent doesn't care about the dimension of your input space. It just walks along the direction opposite to the gradient. It's a one-dimensional walk, so to speak. And this is reflected in its complexity. So projected subgradient descent, where you're getting access to subgradients instead of gradients, and every time you step outside the convex region, you project yourself back within the convex region. This algorithm does find an epsilon optimal point within 1 by epsilon square steps. So the conclusion here is that gradient descent actually beats binary search when the dimension is large, and that's quite impressive. So if we want to know whether gradient descent can be speeded up by quantum algorithms, we need just look over here. So if there is a speed up, then there should be a dimension independent quantum upper bound that is better than 1 by epsilon square. What do we know about the optimality of gradient descent? We know that it's the optimal deterministic algorithm in large dimensions. This was known for 4 decades now? I guess so. It's also the optimal randomized algorithm, although the work here is a bit less than done in the deterministic case, and we know this only when the dimension is large. So in our paper, we actually reprove this result and show that when the dimension is as small as 1 by epsilon square, it still is the optimal randomized algorithm. For the quantum setting, there have been some recent works in convex optimization, but they have been in slightly different regimes. So, for instance, it was known that through a dimension-dependent work by Chakrabarty, Childs, Lee, and Wu, it's a corollary of one of their theorems that quantum algorithms also require at least 1 by epsilon queries for dimension-independent convex optimization. And we prove that, in fact, it requires 1 by epsilon square queries. So there is no speed up at all, not even a constant, in fact, over gradient descent. So this is the introduction to what our work does. And now we'll move on to some technical details. Let's see how the lower bounds look. Both our lower bounds follow a similar theme, so that's easier for me to explain. We want to find functions that encode some kind of information, in the sense that if you find an epsilon optimal point for f, you've actually learned the encoded information. Then you want to say that every query accesses this information in a very controlled manner, and this gives us a handle to say that you actually need a lot of queries in order to learn all of the information. So let's start with the randomized lower bound. This function class that we use has been used, again, for many decades, but we're going to show a pretty strong lower bound for it. So it starts with a base function, which takes an n-dimensional input, and it outputs the maximum of the coordinates. The minimum value that this function takes in the unit ball is negative 1 over square root n. And it takes this value at the point where all the coordinates are negative 1 over square root n. If you query the subgradient oracle of f, what it returns is just the direction of the maximum coordinate. So if the maximum coordinate is xi, then ei is actually a subgradient. Now this is just one function. So if you're trying to minimize it, you don't need to query anything. You can just point out that, oh, the minimum happens over here. So we're going to need a function class over here. And we do that, we create a function class of 2 to the n many functions, where the difference between the functions is that some of the coordinates are flipped. So it's the same as the base function, except that some of the coordinates are flipped, and which coordinates are flipped are specified by this string z. The minimum is still the same, and it's taken at the same point, but with the coordinates flipped appropriately. And we set epsilon to be 0.9 by square root n. So a consequence of this is that if you have an epsilon optimal point, its function value is negative. So this function class encodes the string z in the sense that if you find an epsilon optimal point, you've also learned z. Because if xi ever has the same sign as zi, then the function value is positive, and so it's not epsilon optimal. So if you have an epsilon optimal point, you can look at the signs of xi and just read off the string z from it. How about what the query gives us access to? Well, when we make a query x, what we do is we're sorting the coordinates of x by absolute value in descending order. We're finding the first coordinate where xi has the same sign as zi. And if z is a uniformly random string, we should expect this to happen pretty soon, because each coordinate has a half chance of having the same sign. And the output that we get from the oracles are the absolute value of xi and the subgradient ei, which reveals no information about the later coordinates of z. So if we take z uniformly at random, we're learning around 2 bits per query, and so we need omega n queries in order to find an epsilon optimal point. And that's an omega 1 by epsilon squared lower bound. However, if we look at the quantum algorithms, we do have a quantum algorithm that can speed up this process at least quadratically. And the way to see this is that we can implement an OR query on z with a single query to f. And we can then use Belov's algorithm to learn z using square root n many OR queries. So what function class do we need for a quantum lower bound? In a recent paper a couple of years ago, Bubek, Zhang, Li, and Sitford showed a lower bound on the highly parallel convex optimization problem, where you're allowed to make non-adaptive queries in a round, and you're asking how many rounds do we need. And the techniques that they use they seemed quite useful in order to prove a quantum lower bound, and they did prove useful. So our function class is almost the same as their function class. And this has been used in previous works in past decades, but the techniques that were used now are pretty helpful for quantum. So the function is similar to our previous function, except in 2 major ways. One is that although the input is still an n-dimensional vector, the maximum the term where we're taking the maximum here only has k terms in it. So even though it's an n-dimensional vector, we're just taking the maximum of k components of it. The second difference is that we're subtracting a small constant gamma. And as we go through the maximum, the number of times we're subtracting it increases. This, since gamma is small, doesn't change the global properties of f. So f's minimum is still approximately -1 by square root k, and it takes it at a point very similar to the points we've seen earlier. So what's the function class that we get from the base function? For this, we look at k orthonormal vectors in an n-dimensional space, and we think of n as being really large. And we use these vectors in order to replace x1 through xk. So instead of x1, we have v1 inner product x, and so on till vk inner product x. Apart from that, it's the same function. And another way to look at this function is that we're rotating our input uniformly at random in n dimensions before then applying the same function on it. So it will have the same global properties. Its minimum will still be at minus 1 by square root k, and the point will be the same point appropriately rotated. We set epsilon again to be 0.9 by square root k, and this ensures that the function value at the for any epsilon optimal point is still going to be at least minus, well, at most minus 0.1 by square root k. This function class encodes the set V, although in a certain sense, and that sense is that if you find an epsilon optimal point x, what you've actually done is you found an x which has a non-trivial component along each of the VIs. So if your point x is epsilon optimal, at least, and each of these points, how do I put this? So if your point x is an epsilon optimal point, then none of these VI inner product x terms can be much larger than minus 0.1 by square root k. They should all be smaller than minus 0.1 by square root k. And if you just take a random x, VI inner product x is going to be around order 1 by square root n. And since n is really large, this is a trivial correlation, and we need a much larger correlation with VI in order to be epsilon optimal. And the query access to our VIs is that VI is nearly unknown before the ith query. If you've made I-1 queries, you practically don't know VI. So these 2 points in conjunction with each other would mean that you need k queries, because if you've only made k-1 queries, vk is unknown. And if vk is unknown, then you only have 1 by square root n correlation with vk, whereas you need it to be much larger. So what do I mean by vi is nearly unknown before the ith query? Suppose you know v1 and v2, and you know nothing else about v3 through vk. So they're still uniformly at random from an n-2 dimensional space. If you take any x in the unit ball, with high probability, vi inner product x is going to be around order 1 by square root n, because vi is uniformly at random from a high dimensional ball. And with exponentially small probability, it's going to be as large as log n by square root n. And we can keep n large enough so that this is smaller than gamma. So with high probability, each of our v3 inner product x, v4 inner product x, and so on are much smaller than gamma. And so if we look at these terms starting from the third term, v3 inner product x minus 2 gamma is approximately minus 2 gamma. v4 inner product x minus 3 gamma is approximately minus 3 gamma. So this is the order of the later terms, apart from v1 and v2. So how does this give us a quantum lower bound? We go through the hybrid argument to reach there, and it's a pretty neat argument. So suppose you have a k-1 query algorithm that you claim is doing well on this task. Your first query, you're going to create a superposition of inputs. So here the inputs are xi. You've created a superposition of xi, and you're going to pass it to the function value oracle. Now before you pass it to the function value oracle, I'm going to change the oracle to a different oracle which only has information about the first term of the maximum. So in this case, it's just v1 inner product x. And you have a right to be annoyed that I've switched out your oracle, but you can't really claim that your algorithm is spoiled because I switched out the oracle. This is an inconsequential change. Since we don't know what v1 is, we don't know v1 through vk, it's highly probable that, in fact, with high probability, v1 inner product x is going to be the maximum term. So for most of the inputs in the superposition, they're not going to notice a difference whether I use the original oracle or this modified oracle. And so the output states after going through this modified oracle is going to be very close to the output state if it had gone through the original oracle. And since quantum algorithms or any quantum process is made out of unitary rotations, the fact that the output states are close after the first oracle call is going to imply that the output states are the same at the end. So if you run this algorithm through to the end, the final quantum states that you have are still going to be close because you always had distance preserving transformations in the middle. And what this means is that your output itself is going to be close in total variational distance. So, alright, you've accepted that this is an inconsequential change, and you've decided to put it in the past and go through the second query. Now the second query, you've done some operations. Again, you're going to pass it through Oracle, and again, I replace it with this limited information Oracle, where it's only limited to the first two terms of the maximum. Now, since the first Oracle that it went through didn't have any information about V2 and so on, before you pass through the second query, V2 through Vk are still completely unknown. And again, what that means is that the second term is going to be larger with high probability than any of the later terms. So again, this is an inconsequential change. And again, you can argue that if your algorithm was correct, the original algorithm, then these changes are hardly making any difference. It should still be correct. And we can do this for k-1 queries. After k-1 queries, the argument still holds that the outputs of the original and the modified algorithms should be pretty much the same. But notice that the k-1 times changed algorithm, the algorithm where I've switched out the oracle k-1 times, it's completely independent of Vk. All the oracles were completely independent of Vk. And what this means is that this algorithm cannot output an epsilon optimal point because its correlation with Vk is going to be trivial. So what this means is that the original algorithm also is not going to have an epsilon optimal output. And that concludes the lower bound. You do need k queries in order to find out what Vk is and output an epsilon optimal point. It turns out that projected subgradient descent does also accomplish this task in k queries. And if you look through the details, it doesn't actually use any projections, and it queries only smooth points. So it's basically gradient descent itself that has done it in k queries. And this is a pretty convincing way to say that there is no quantum speedup over gradient descent. The actual function that we use is actually slightly modified because we might query outside the unit ball as well, and we want to account for those. It's a small modification, and I'm not going to go into it here. Other points of note is that the n actually doesn't have to be really large. It can be as small as 1 by epsilon to the 6. And with the modification that's actually taken from the same Bubeck et al. Paper, you can bring n down to 1 by epsilon to the 4. So what does this leave as open questions? Well, the main one is, what is the quantum complexity of convex optimization in small dimensions? It's still open that for n smaller than 1 by epsilon to the 4, there is a quadratic speedup. What other classes of convex optimization problems would get quantum speedups? We know that there are convex optimization tasks like semi-definite optimization that do get quantum speedups, and we know that our first randomized lower bound did also get a quantum speedup. But we don't really have an idea of when exactly you do get quantum speedups and when you don't. So some clarity on that would be nice. And in particular, this very function class here, where we don't put the gammas, but we do put the vectors v1 through vk. For this function class, what is the quantum complexity? We know a lower bound of order square root k, omega square root k, and we have an upper bound, a simple upper bound of order k, but we don't know where exactly it lies. That is my talk. Thank you for listening. Goodbye.